Hello everybody. So in this lecture I'm going to try to tackle hybridization, and after I'm done with the hybridization I will switch to a trigonal bipyramidal geometry and octahedral geometry. Okay, we start with molecule like CH. We can go CH4 or let's go with CCl4. And let's practice loose structure of this molecule. The way we do it, we said we have 1 carbon plus 4 chlorines. So valence electrons for this molecule, it will be 1 multiply 4 for carbon and 4 multiply 7 for chlorine. So totally we're dealing with 32 electrons. Okay. I have 32 electrons. We say electronegativity of carbon is less than electronegativity of chlorine. So based on this, carbon has to be the central atom. Here is carbon. We have 4 chlorines, so you can put the 4 chlorines around it. And then use 2 electrons per each bond. Okay. So I'm using 8 electrons to make 4 sigma bonds. Okay, so I'm going to say minus 8. Okay, because I used 2 for each bond and I made 4 of them. So now we are plus 24 electrons. Again, we refer to the electronegativity. Chlorine has higher electronegativity than carbon. So if you do have extra electron, give it to the outer atom and make it active. Chlorine has 1 and is going to gain 1 through sigma bond, so 2 is missing. 6 to be 8. So I'm going to give it 6. Okay, now it's active. You want to draw a circle around it. You ask yourself that how many electrons do I see in this circle? I do see 7, so I say 7 plus 1 through sigma, 8. Okay, so I say minus 6 electrons. And I do the same thing for other chlorines. So I use 6 electrons, and I do have 4 chlorines, so I use all the electrons. Okay, as I showed you, chlorine is acted. How about rest of chlorines? They will be acted similar to this one, similar to number 1. If you check carbon, we see 4 electrons inside the circle, so we say 4 plus carbon made 4 sigma bonds, so it's going to gain 4 electrons through the 4 sigma bonds. Carbon also is active. Formal charges, if you practice formal charges, you go with, this is a chlorine, it's a group 7, minus, we see 7 electrons inside the circle, 0. You get 0 formal charges for each. How about carbon? Carbon is a group 4, okay, minus, I see 4 electrons inside circle, 0. So carbon has 0 formal charge. Okay, when you add all the formal charges, they will be equal to the charge of this molecule, which is 0. Okay. We said, and the way we figure electron geometry and molecular geometry, we go with pairs of electron around the central atom. So when it comes to electron geometry, we go with the sigma lone pair around the central atom. So I go with sigma and lone pair on carbon. Okay, so sigma for carbon. Carbon, it has 4 sigma, lone pair around carbon, 0. Got it. This one is equal to 4. That means electron geometry, it will be tetrahedral. Okay, tetrahedral. And because the sigma plus lone pair, we got it equal to 4. Okay. Next one, how about the real or molecular geometry? This one also too will be tetrahedral. And we said if lone pair on the central atom is equal to 0, if lone pair on the central atom is equal to 0, you go with this. Electron geometry, it will be equal to the molecular geometry. And in this case, both of them, they will be tetrahedral. Okay. The way we show this one, like in 3D, we go with, here is carbon, we have one chlorine, and the second one will be inside the plane. The third one is pointing out of the plane. Okay, and the fourth one is back of the plane. Okay, this or the screen. So we make this one bold. Put the chlorine here. And that one usually we put like kind of dashed line. So this chlorine is back of the screen. So 1 and 2 inside the screen, 3 out of the screen, and the 4th back. And remember, you do have lone pairs on each chlorine. And I'm not going to show them right now because I'm trying to save time for myself. What's the bond angle between them is 109.5 degree. Okay. We say this is perfect tetrahedral geometry. Okay. This is perfect tetrahedral geometry. And the central atom is carbon. Carbon has 6 protons and 6 electrons. If we want to write electron geometry, electron configuration of carbon, it will be 1s, 2, 2s, 2, and 2p, 2. So the first orbital, which is s, is full. The second orbital, again, is full. And the third orbital, the p orbital, it has 1 electron and first 2 or p orbitals, and the third one is empty. Okay, so if our central atom is supposed to make 4 sigma bonds with the chlorine, has to use this s orbital, s and p orbital, to do interaction with the chlorine. But the problem that we see right now, the 2s orbital is full, so already taken by electrons of the carbon. So this one cannot be used by carbon to do interaction or sigma interaction with the outer atoms. How about those two? Yes, we can use them. So carbon is going to share these 2 electrons to make 2 sigma bonds. So we can make 2 sigma bonds, that's fine. But the question is like, how can we make 4 of them instead of 2? Okay, so this one does not give us the right answer when it comes to, number of sigma interaction with the central atom. And the way we actually describe this one, we go through a hybridization. In hybridization, okay. In hybridization, we said, as Linus Pauling said, he said, when we want to build molecule, we don't use atomic orbitals. When we say atomic orbital, I'm talking about orbitals like s, p, d, and f. We call them atomic orbital. He said we don't use those to do interaction with outer atoms. Actually, we mix those orbitals. We mix the atomic orbital to make new orbitals that we call them hybrid orbital. So let's say in CCl4, okay, we need to have 4 singly occupied orbitals to make 4 sigma bonds. And the way carbon is going to do it, so carbon, it has, we said, 1s orbital with 2 electrons. Here is 1s orbital. Then you have 2s orbital with 2 electrons. Then you have the 2p orbital, okay, 2p orbital, and it has only 2 electrons in it. And Pauling said, in order to make 4 singly occupied orbital, you need to take this electron, the one that is pointing down. You need to take it and shoot it to higher orbital. Okay. Remember, as we go up, sorry about this one, energy is increasing. Okay. So what we need to do, we need to take the electron, shoot it to higher orbital, and not only we are sending to higher orbital, we need to flip sign up this electron. So the first one stay as it is. We have 2 electrons in it. We call it 1s2. And then the 2s, now we have only 1 electron in it. And the 2p orbital, okay, we have 3 electrons. And the third one came from the 2s orbital. And check the direction of this electron. Now it's pointing up. Okay. And so right now I have 1s orbital that is singly occupied and a 3p orbital also singly occupied. I need to have 4 singly occupied orbital, and I do have them. But remember that when we build the geometry, sorry about that. When we build the geometry for this molecule, we said all these bond length and bond angles are equal. But right now, as you see, we have one orbital that is 2s, and we have 3p orbital, and they are not going to be exactly the same. So if you use this orbital, it's not going to give you the same bond length as the 2s orbital. Okay. When it comes to hybridization, what we do, we mix this atomic orbital. So I'm going to say this one atomic orbitals. Okay. I will mix the atomic orbitals to get a hybrid orbital. So now when you mix the 2p with the 2s, energy of the 2p orbital will go down a bit, and the energy of the 2s is going to go up. So you will get new orbital that they are going to be between the 2p and the 2s, and there will be 4. I use 1 from 2s and 3 from 2p, so I'm going to get 4 of them. And you write sp for each. You have 1 electron in each orbital. Okay. Next thing is, you need to write the contribution of the s and p orbital. We use only 1 s orbital, so we say s1. Here, s1 for each. And we use 3p orbitals, so we say 3. We want to say that the contribution of s orbital in each of this is a 25%. So 25% made of s and 75% made of p orbitals. Okay. So now what we got a central atom that it has 4 identical orbitals. Here, I'm going to show them. 4 identical orbitals, and inside each of these orbitals we have 1 electron. And outer atom, whatever the outer atom is going to reach the central atom through these directions. So here is the outer atom. You can call it X. You can call it chlorine, fluorine, whatever. Okay, so I'm going to call it X. X, it can be chlorine in this case. Chlorine is going to share one electron with carbon, and the electron has to be with opposite spin. Okay, or I mean the direction of the electron in this case is pointing down. So we got 4 places that chlorine had interaction with the central atom, with the orbital of the central atom. And each one, we call it here sigma. So we managed to get 4 sigma bonds. The bond angle between this orbital, okay, regardless of what you have as a central atom, regardless of what you have as an outer atom, bond angle between this orbital is 109.5 degrees Celsius. 5 degree. Sorry about it. 109.5 degree, and this one is going to tell you what's the bond angle and what you should expect. So central atom is going to tell you what will be the geometry, what will be electron geometry, and what will be the bond angle, the expected bond angle. I'm going to keep practicing the hybridization. Okay. So we have a couple of things that we need to know. We are dealing with atomic orbitals, S, P, D, F. We have hybrid orbitals like sp, sp2, sp3, sp3d1, and then sp3d2, and I will talk about all of them. Process of mixing atomic orbital, we call it hybridization. Okay, so hybridization is the process mixing atomic orbital. We call it hybridization. And number of hybrid orbitals equal to number of atomic orbitals. Okay. So like previous example, we said we have carbon, 1s2, 2s2, 2p2. We mix 1 from 2s, so we mix 1 from 2s plus 3 from p. Okay, 1 plus 3, you will get 4. Okay. Now you have S and P. Write the contribution for each orbital. From S, we have only 1. You don't need to write the 1, but it's fine if you write it. and from p we have 3. So we got 4 hybrid orbitals, and then hybridization in this case is sp3. Okay. I want to keep practicing the hybridization. So more example, and this time I go with NH3. NH3, it has 8 valence electrons, nitrogen plus 3 hydrogen. You go with 5 plus 3 multiply 1, 8. Never ever put hydrogen as a central atom, because hydrogen has only 1 electron and it can make only 1 bond. So never ever put hydrogen as a central atom. You don't have option, you go with nitrogen this time. So we said never ever put hydrogen. So here, 1 bond. This is the second bond, and that one is the third bond. So out of 8, we use 6 of them. We're left with 2 electrons. We give them the central atom. We call this one lone pair. We made 3 sigma bonds. Okay. So sigma plus lone pair, you go sigma for nitrogen equal to 3. Lone pair, again for nitrogen we have only 1, so we got it equal to 4. Because this one is equal to 4 electron geometry, it will be tetrahedral. So you expect 109 for the bond angle, 109.5. And we went through the geometry of this molecule, and we said in this case, because we have lone pair electron geometry, it will not be equal to the molecular geometry. Real geometry, it will be trigonal pyramidal. Okay. How to find the hybridization? From now, anytime they give you a molecule like this, okay, the way you find the hybridization, if you're not dealing with a transition metal, okay, the way you do with the hybridization, you go with, you say, always we have 1 s orbital, and for the p you will have 3p orbital, and for the d you will have 5d orbital. What do I mean by 1 and 3 and 5? S is made of 1 block, okay, just one. How about the p? P is made of, okay, 3p orbitals. So 1s 3p orbital, and the d orbital is made of here. This is a d orbital, and we see 5 orbitals. Okay, 5 orbitals. Now, this one is a sigma plus lone pair equal to 4 pairs. That means 8 electrons. Okay, 8 electrons. So you need to have 4 boxes to accommodate 8 electrons. First box, you can put 2 electrons in it, 2 electrons here, 2 there, and 2 there. So I need to have 4 boxes to accommodate 8 electrons. And always you start with 1s, and then you go through p, and then you go higher level. So in this case, because I have 4 pairs, I'm going to say I need 1 from s, and I'm going to take the 3 from p, and it will give me 4 orbitals. That's hybridization for them. From s it will be 1, and from p it will be 3. So I got 4 sp3 orbital. This is the hybridization. How did we get this one? We said we mix s orbital. This is s orbital. You mix it with 3 p orbital. Okay. What you got 4 orbitals. You put the central atom in this case is nitrogen. Write the central atom. You got 4 hybrid orbitals. Drop those 4 hybrid orbitals. 1, this is hybrid orbital. 2, 3, 4. So right now I got 4 hybrid orbital. And put the valence electron of nitrogen. Okay, show valence electrons. Okay, so electrons of nitrogen. Show them. Nitrogen is a group 5. So I go with 1, 2, 3, 4, and in this case 5. Okay, this one is full. Okay, this one is full, so that means the central atom is not going to use this orbital to do interaction with the hydrogens, because it's already taken by electrons of the central atom. So this one stay as lone pair. Okay, this one stay as a lone pair. Now I have 3 singly occupied orbitals. That means hydrogen, it can reach nitrogen from these directions. And we will get 3 sigma interactions. Okay. So this cartoon is showing you hybridization. Hybridization is 1, 2, 3, 4, sp3. Okay, we got 4 orbitals, and the contribution is going to be s1 and p3. Okay, bond angle between them said from 109, the perfect tetrahedral, drop it by 2 degrees for 1 lone pair, so it will be 107. And I showed you also the molecular geometry, which is a trigonal pyramidal. Okay. Next example about hybridization will be the water molecule. So water molecule, you go with H2O. So you have O. We have 2 plus 6, 8 valence electrons. So I use 4 of them, and the rest I will put them on oxygen. Hydrogen, it has 1, and it got 1 through sigma 2. Okay. Formal charge is 1. I see hydrogen is a group 1 minus, I see only 1 electrons inside circle, 0. Oxygen, I see 6 electrons plus 2 sigma, 8. So oxygen is acted. Oxygen is a group 6 minus, I see 6 electrons inside the circle, 0. So the formal charge for oxygen is 0. We don't have sorry, in this case we do have lone pair actually. We have 2 sigma on oxygen and 2 lone pair. Again, on oxygen, 4, because it's 4, so because this one is 4, that means we have 8 electrons. And electron geometry, it will be tetrahedral. Electron geometry is not going to be equal to the molecular geometry because we have a lone pair. Molecular geometry we said is bent. Okay, we have 4 pairs. Again, you say S, 1s plus 3p plus 5d. Okay, make the hybridization. You need to accommodate 8 electrons, so you go with 1 box from S plus 3 from P, and you'll get 4. Write the contribution S1 and P3. Okay. Again, you're using 1 from S, 3 from P, and you get oxygen. You get oxygen with 4 orbitals. Okay. 4 sp3. 1, 2, 3, 4. Show electrons of central atom or oxygen. Oxygen is a group 6. I'm gonna put 1 electron inside each orbital. Use 4. I need to accommodate 2 more, so I put them 2 here. Okay. This orbital will be a lone pair because it's taken by electron out the central atom. And same thing here. We call this one lone pair. That means hydrogen can reach the central atom only through these 2 directions. You put hydrogen there, hydrogen, and you show them as sigma bond. Okay. Bond angle, we said from perfect tetrahedral, which is 109, drop it by 2 degrees per lone pair. We have 2 lone pairs, so it will be something around 104.5 or 105. Okay. So I think we practice enough about the hybridization of small molecules, and we can go with trigonal bipyramidal geometry or octahedral. Discuss that one, and then we can talk about the hybridization also. Okay. So till now, remember we said we have a central atom with central atom A, and B is the outer atom. We practice AB2, and then we switch to AB3, and after that one I want to AB4, which is tetrahedral. Okay. This slide, I'm going to go through AB5. An example is going to be something like P is the central atom and Cl5 is the outer atom. Okay. Let's calculate valence electrons. We have 1 phosphorus plus 5 chlorines. So we go with 5 plus 5 multiplied 7. Okay. We have 40 electrons. Electronegativity of phosphorus less than electronegativity of chlorine. So phosphorus is the central atom. You go phosphorus, and you have 5 chlorines. You put 3 of them inside the plane. Okay. So I put this 3 set as a plane, and 2, I put them in axial position, up and down. So minus, we say we made 5 sigma bonds, and we use 2 electrons for each bond, so it will be plus 30. Yeah, 30 electrons. Give the electrons to outer atoms and make them octet. Okay, so minus 5 chlorines, and I gave each chlorine 6 electrons, 0. Cool. So we got chlorine octet. Check chlorine. Chlorine, I see 7 electrons plus 1 through sigma 8. How about the formal charge? Chlorine is a group 7 minus, I see 7 electrons inside circle, 0. So we got the formal charge 0, 0. Okay. Check the central atom. Phosphorus. Okay, I'm gonna write it here. Phosphorus, I see 5 electrons. So I say 5 for phosphorus. And we made 5 sigma. And now is 10. Okay. We passed the octet rule. Or we passed the octet. Okay. So phosphorus is not following the octet rules in this case. And remember, we said if we have element from third period, when n is equal 3, n means the period. Okay. When n is equal 3, you will have atoms that they can follow octet rules, but don't be surprised if they, if they don't, or if they form more, bonds, more than 4 bonds. So then they will have maybe 10 or 12 valence electrons. Okay. It's not wrong. They can do it because they do have higher orbital, and we call it d orbital. Okay, let's talk about the geometries. We have 5 sigma, and we have 0 lone pair, on phosphorus. So we got this one equal to 5, and we do not have lone pair, so electron geometry is going to be equal to the molecular geometry. And now what's the electron geometry? I said we put 3 of them inside the plane. Let's call it 1, 2, 3. These 3 chlorines, if you connect them, okay, you will get triangle plane. Okay, so this one is a triangle. Okay, so I'm gonna say trigonal. Okay. Trigonal. And next thing, if you connect the axial atom, any of this axial chlorine, so they are taking the axial position, and chlorine number 3 or 2, they are taking the equatorial position. If you take any of this atom, the equatorial position, and connect it to the axial, you will form a pyramid. Okay, you can form pyramid with number 4, 1 pyramid, and you can do the same thing when you connect the atoms to the one that is sitting down, or number 5. So we can get two pyramids, okay? And this is our plane, or the base, okay? The base of pyramid. Okay. A base is made of three, that I'm gonna call it trigonal. I do have two pyramids, so I'm gonna say trigonal by, okay, trigonal by pyramidal. Okay, trigonal by pyramidal. Trigonal because I have a base that made of three atoms. I call it trigonal or trigonal, and I have two pyramids, so I say bipyramidal. Okay, what's a bond angle? You have two bond angles. Okay. Again, I will write it here. Bond angle between the equatorial chlorines is 120, and the bond angle between the equatorial chlorine, it will be 90. So as I said, we have two bond angles. Question now, what's the hybridization? Okay, hybridization, we have five pairs of electrons. That means we are dealing with 10 electrons. We need to accommodate 10 electrons. You go with 1 from S, plus 3 from P, plus 5 from D. And you want to accommodate 10 electrons. So I need to have 1 from S, 3 from P. So till now, 1 plus 3, 4. I'm missing 1. And I'm going to use 1 from D. And the hybridization, it will be S, P, 3, D, 1. Okay. How many orbitals, hybrid orbital did we make? We made 1, 3, 1 here, 5. So we made 5 SP1, S1, P3, D1, and orbitals. Okay. Okay. So I said the hybridization is going to be S, P3, D1. And we made 5 of them. Okay, 5 of these orbitals. Here is our central atom is phosphorus. Okay. You're going to use 1 from S plus 3 from P orbital. So you go 3 from P, and you will use 1 from D. This is 1 from D. What you'll get phosphorus with 5 hybrid orbitals. 1, 2, 3, 4, 5. Okay. Now, chlorine. Sorry, before we put actually, or we start talking about chlorine, let's put the electrons of the phosphorus. Phosphorus is group 5. Show the electrons, valence electrons of phosphorus, group 5, and put 5 electrons there. Okay, now time to talk about chlorine. Chlorine will reach the central atom through these directions, 5 directions. We have 5 singly occupied orbital, so we can make 5 sigma bonds. And this is hybridization of trigonal by pyramidal geometry. trigonal bipyramidal geometry. Bond angle we said between axial and equatorial 90. Between those two it will be 120 degree. Okay. So I practiced AB 5. An example was PCL 5. Now keep it AB 5. Okay, AB 5 family, but I will not have 5, 5 outer atoms. So I will have 4 plus 1 lone pair. An example, we can go with SF4 PCL4 minus 1. Okay, it doesn't matter which one. You should practice. Okay. So let's say SF4, you go with 6 electrons for S plus 4 multiplied 7 for fluorine. So we have 34 electrons. Okay. 34 electrons. And electronegativity of sulfur less than fluorine. Fluorine will be the outer atom and sulfur is the central atom. So I go with, so put it here, sulfur, fluorine, fluorine, minus 4 sigma, and we use 2 electrons for each. So 26 electrons. Give each fluorine 6 electrons to make it octet. So minus 4 fluorines, and we give each 6. So it will be plus 2 electrons. You don't have any option. You put it on the central atom. Okay. And this one is going to be a lone pair. Okay. Lone pair on sulfur. Time to write the sigma and lone pair. For the central atom, I see 4 sigma on sulfur, and I see 1 lone pair on sulfur. I got this one equal to 5 because it's equal. This one is equal to 5 electron geometry. 2 will be trigonal or trigonal bipyramidal. Bipyramidal. And hybridization, because we have 5 pairs of electrons, is going to be sp3d1. Okay, electron geometry is not going to be equal to the molecular geometry. Okay, and I need to talk about the molecular geometry. Okay, I had 2 options for the lone pair. One is to put it in equatorial position, the second axial. So I could draw this. I could say sulfur, fluorine, and the lone pair, I'll put it there. Or I go with this. Now we need to talk why we decided to go with the second instead of the first one. Okay. First one, we put the lone pair in axial position. Okay. Axial position. Let's look to the bond angle. Here, bond angle is 120. Okay. Bond angle between axial and equatorial is 90 degree. So when you put the lone pair in axial position, you will build 190, 2, 3. So we have 390. Okay, 390 degree, repulsion between lone pair and bond pair. But in this case, when you put it in equatorial, you will have 190. And that's the second 90. So instead of 390, we got only 290 interaction, 90 degree interaction between lone pairs and bond pairs. Okay. If you can increase the bond angle, so if you can increase the bond angle, you will reduce the repulsion. Okay, this is a fact. Okay, when it comes to the lone pair is close to the central atom. Because it's close to the central atom, it will take more space and it will have a strong interaction with any bond pair close to it. We try to give it more space. If we put it in equatorial position, the gap between this lone pair and another one that is in equatorial, it will be 120 degree. Okay, so we have 120 degree, two of them, and we have only 290 degree interactions. Okay, the less 90 degree interaction you have, the more stability you get. And so that was the reason that I decided to go with this. And this, I said this one is wrong. Okay. Next example about hybridization and also the geometry of the trigonal bipyramidal is going to be the AB3 with 2 lone pair from AB5 family. Okay. And I go with PCl3 minus 2 or BRF3. Okay. So the first one, PCl3 minus 2, you go with 5 electron for phosphorus plus 3 multiplied 7 for chlorine, and we have negative charge, so we add 2 electrons. So we have 42 electrons. Chlorine, it will be the outer atoms because it has higher electronegativity than phosphorus. The one that is electropositive, it will be the central atom. Here is phosphorus. Now I need to put the chlorine around it. 1, 2, 3. I use 6 electrons. I'm going to give each 6 electrons to make it octet. Minus 18. Okay. And I'm left with, okay. Sorry, this one is not my bad. This one is wrong. It is 28. 28 electrons. Sorry about this one. It's a bit too late. Right now is 2:50 a.m. and I'm working on this this lecture, so forgive me please if I make some silly mistakes. Okay, so we said we use 6, 22, and then I use 16 of them, so it will be plus 4 electrons. Okay, I'm gonna give these 4 electrons to phosphorus, so phosphorus will have 2 lone pairs. We go with 3 sigma for phosphorus, 2 lone pairs. Again for phosphorus, we are dealing with 5. That means we have 10 electrons. We need to have 5 orbitals. You go with 1 from S, 3 from P, plus 1 from D, and you get 5 orbital of S1, P3, D1. Okay. I put the 2 lone pairs inside the equatorial position. Again, why? Because the bond angle between them, it will be 120 instead of, if you put it in axial position, it will be 90 degrees. So I prefer to put it inside the equatorial position. Now, electron geometry, it will be trigonal, trigonal, bipyramidal, but the real geometry, if you cover these 2 lone pair, you will see a T. So this one, it will be T shape. Okay. T shape. Okay. We have something else about this one. I need to show the hybrid orbitals. I said we are using 1 from S, 3 from P, and 1 from D. So we get 5 orbitals. And the central atom, phosphorus, with 5 orbitals. Okay. 1 from S, 3 from P, and 1 from D. 1, 2, 3, 4, 5 orbitals. Phosphorus is a group 5, so I'm going to show the electrons of phosphorus. Five electrons until now. Please look to the charge. Charge says -2. That means we have extra 2 electrons. So I have 2 extra electrons, and I need to show those 2 extra electrons. And I go with, you pair that one. Sorry, I should not actually put it there. Ignore this one. Need to put it here. So this one, it will be lone pair, and the second one I will put it again inside equatorial position. That one also, it will be lone pair. Okay. So here we have only 1 electron inside that orbital. Okay. Your outer atom can reach the central atom or phosphorus through those 3 positions. Our outer atom is a chlorine. It will come with 1 opposite electron. And we will get 3 sigma bonds. Okay. we can add another lone pair, and we can go with AB2 E, 3 lone pairs, PCl2 minus 3, or xenon F2. Xenon F2, you go with 8 for xenon plus 2 multiplied 7, and that's going to be 22 electrons. Okay. Xenon is the central atom because it has less electronegativity. Sorry, xenon, it will be the central atom, so I put here xenon. I have only 2 fluorines, 1, 2. I will use 2 electrons for each bond to make sigma, 2 sigma bonds. Okay. So minus 4, we're plus 18. Give each fluorine 6 electrons and make it octet. So minus 12. Now we are plus 6. You don't have any option. You give xenon 3 lone pairs. 1, 2, that's the third lone pair. So we have 2 sigmas and 3 lone pairs on xenon equal to 5. Because it's equal to 5, we are dealing with 10 electrons. So the hybridization, it will be S1 plus 3 from P plus 1 from D. It will be SP3 D1. Okay. And mix S plus 3p plus d orbital, 1d orbital. And we get 5 sp3d1. Central atom is xenon. 1, 2, 3, 4, 5. Show electrons of the central atom or xenon is a group 8. So I use 5 of them. Now I need to pair some electrons, and I start with the equatorial position. Okay, 6, 7, 8. So we have 3 lone pairs. And after atom can reach the xenon only from these directions. And you will get 2 sigma bonds. If you cover lone pairs, only thing you get just a line. Okay, we call this one linear geometry. So the electron geometry, because this is, we got it equal to 5, it will be trigonal pyramidal, so bipyramidal. But the real geometry, the molecular geometry, it will be linear. Okay. So I'm done with this family. Now I will switch to the octahedral, and I will try to do 2-3 examples about octahedral and finish the lecture. I think I need more paper. Okay. And from the octahedral, I start with the here AB 6, example SF 6. We have sulfur plus 6 fluorines, so we get 6 plus 6 multiplied 7. We get 48 electrons. 48 electrons. Electronegativity of sulfur less than electronegativity of fluorine. So sulfur, it will be the central atom. Here is sulfur, fluorines, I have 6 of them. Bond angle between all, it will be 90. But before we talk about the bond angle, let's show the rest of the electrons. Let's give each 6, make it octet. Okay, so I use all the electrons to make 6 sigma bonds, and all fluorines are octet now. So we go sigma on sulfur equal to 6, lone pairs for sulfur 0, got it equal to 6. Electron geometry is going to be equal to the molecular geometry because we don't have a lone pair, and both there will be octahedral. Okay, now back to the lone pair. Lone pair, doesn't matter which fluorine you pick, it will be equal to 90 degrees. Easy way to remember the geometry: if you connect this 4 fluorines, okay, you will have a base that's made of 4 fluorines and 2 inside the axial position. It doesn't matter really which fluorine you choose, or you decide to go with as a base. Always the bond angle is going to be 90. Hybridization, yeah, you have 6 sigma, so you're dealing with 12 electrons. You need to accommodate 12 electrons. You go with 1 from S, 3 from P, until now we got 4. We need 2 from D, so we will get 6 orbitals of S, P 3, and D 2. Sulfur with 6 hybrid orbitals. So this one should be bigger. So I'll put 1 electron inside each orbital. Next, I will show the outer atom. Outer atom, it can reach the central atom through these directions. So I got 6 sigma bonds. That's the way you get them. Okay. So we have the electron and molecular geometry. Both are octahedral. The bond angle, and doesn't matter how you look to the system, from which side you look to this geometry, bond angle is going to be 90 degree. And hybridization is sp3, d2, and we have 6 hybrid orbitals. Okay. Next one, I go with AB5, but I will add one lone pair to it, and I go with SF5 minus 1 or BR-F5. So if we go with SF minus 1, SF5 minus 1, so 6 for fluorine, 5 multiplies 7, so 6 for sulfur, 5 multiplies 7 for fluorine, and we have 1 extra electron, so you will be dealing with, okay, 42, hold on, this one, I feel this one, something is wrong with it. 42. Okay, my mind is going down. It's not working properly. Okay, so we got 42 electrons. And please forgive me about it. Okay, sulfur is the central atom. Here is sulfur. Fluorine. It doesn't matter where you put the lone pair in this case, because all octahedral positions here, the previous one, all of them are identical. So just replace one of these fluorine with a lone pair. It doesn't matter whether you put it here or there, they will be the same. Okay, and one here. So I will have lone pair somewhere there. Okay, minus 10, it will be 32. Give each fluorine 6 electrons. Minus 5 multiplies 6, it will be plus 2. And you show them lone pair and sulfur. Okay, so now what did we get? We got 5 sigma on sulfur, 1 lone pair on sulfur, equal to 6 electron. Geometry, it will be octahedral. Electron geometry, it will be octahedral. Electron geometry is not going to be equal to the molecular geometry because we have a lone pair. Okay, because we have a lone pair, they're not will be equal. Now, I'm gonna just we said it doesn't matter where we put the lone pair. I wish that I put the lone pair here, because it will be easy to, to figure the geometry. And I'm just gonna rotate this one. Okay, I will rotate it so it will show up there, and in that case you will get sulfur lone pair. It will be here, so I'm moving this one down. I will have 2 fluorines here, 2 there, and 1 fluorine there. Show the lone pair for each fluorine. Okay. So now, if you look at the geometry, you see 4 of the fluorines will form a base for you. At that base, it will be square. And there will be 1 axial fluorine standing or sitting on this plane. So geometry is going to be square. Okay, square because we have a base that made of 4 and they are identical. Now if you go and connect any of this atom, any of the atom of the plane with the axial atom, when you connect all of them to the axial atom, you will get a pyramid. And the base of this pyramid, here, this base is a square. So we say square pyramidal. Okay, square pyramidal. What's the hybridization for it? Hybridization, we have 5 sigma plus 1 lone pair 6, so it will be sp3d2. How about 1 more lone pair? Now if you want to add 1 more lone pair to this system, try to put the lone pair way far from the first one. First lone pair, we said you can put it anywhere. We put it here. The second lone pair, do not put in this position, because if you put it here, the bond angle between them, it will be 90 degrees. But if you put it in the axial position here, it will be 180 degrees far from first one. So I will put the second lone pair in this position, in this axial position, to be way far from the first one. And here example, AB 4, E2. Okay. An example for it, you can go with SF4 minus 2 or xenon F4. Okay. Xenon F4, you have 8 electrons for xenon plus 4 multiply 7, so 28 and 8 there, you get 36 electrons. Okay, 36 electrons. Xenon, again, is the central atom because the electronegativity of xenon less than fluorine. So I go with xenon. I have fluorine, 4 of them. Here 4 fluorines. Give each fluorine 6 electrons. So minus 8 electrons for 4 sigma minus 6 multiply 4. Okay. So totally we use 24 and plus 8, 32 electrons minus 36 plus 4 electrons and put the first lone pair axial position. A second lone pair, it will be cross of the first lone pair. Okay. We have 4 sigma. Okay. 4 sigma on xenon. We have 2 lone pairs on xenon. So total we are dealing with 4. Electron, sorry, we are dealing with 6 electron geometry. It will be octahedral. Okay. And let's figure the molecular geometry. You connect this fluorines. When you connect them, you get a square. So I say real on the molecular geometry, it will be square. And we don't have any axial atom. It's completely flat. So it will be a square planar. Okay. What's a hybridization? You have 6 orbitals. I said electron geometry is octahedral. Because it's octahedral, it will be sp3d2. Okay, so I'm gonna stop the lecture here. Hope this one was useful for you guys, and please forgive me so that sometimes I made a mistake with the adding. It's too late. It's 3:18 in the morning, so right now is at 3:18. And my mind is not working properly. I can't get enough time during daytime because of the baby. I need to do my job, need to do the babysitting, and so this is kind of like the best time for me actually to get back to my actually job and do something about them. Okay, take care guys, bye.